So this lecture is an introduction to the concepts covariance, correlation, and independence. It's an introduction in the sense that we'll look at some properties of these terms, but we are not going to give the complete definitions here. So let's start with covariance. The idea now is that we have two random variables. So x and I are just two given random variables. Could be discrete, could be continuous. Then the covariance between them is denoted by COV for covariance x comma y. And it makes no difference if you do covariance of x comma y or y comma x. And what it is, it's basically a measure of the degree to which they are linearly associated. So the random variable x can take a bunch of values, the random variables y can take a bunch of values. If it's the case that whenever x tends to be high, y tend to be high, and vice versa, then it has a positive covariance. We'll look at a better example later on in this lecture. So even though we're not going to talk about the actual formula for the covariance, we'll look at least one simple example where we will calculate the covariance, and that will provide us with most of the intuition that we need. So I have two random variables, y and x. X random variable can take two values, -1 and 1, so that's in the first row, while the y random variable can also take two values, -1 and 1, and that's in the A column. These four numbers represents the probability of each possibility. So 0.25 in cell B2 tells us that there is a 25% probability that y will come out to be -1 and x will come out to be -1. Similarly, there's a 25% probability that y will come out to be -1 and x will come out to be +1. If I sum these probabilities vertically, so I do equal B2 plus B3, I will get the probability that x is equal to -1. Because x can be -1 in two cases. It's -1 when here, when x is -1 and y is -1, but it's also -1 here, when y is +1. So this 0.5 tells us that the probability that x will come out to be -1 is 50%. If I do the same thing, I also have a 50% probability that x is equal to +1. If I sum these horizontally, B2 plus B3, then in this cell I have the probability that y is -1. And similarly, I have here, well, I did that incorrectly. It should be B2 plus C2, of course, summing vertically. So this is the probability that y is -1. Copy this down. I don't know why it doesn't want to stick. B2 plus C, not C3, C2. That's the way it should be. If I now copy this down, this should be 0.5 as well. Yes. Probability that y is -1, probability that y is +1. So from this, we can easily find the expected values. So the expected value of x is then this number here. It can take -1. So let's do an equal to this times the probability that it takes the number -1 plus it can take the value +1 times the probability it takes that value. In this case, -1 and 1 are equally likely, so the expected value will be the average of -1 and 1, which is 0. Similarly, the expected value of y is, let's change this to y, is then equal to, can take -1 times this probability plus 1 times this probability. So that will be 0 as well, at least the way we've set it up. But now we can also manipulate these four probabilities and change these to anything we like, as long as they sum up to 1, because, well, one of these four cases must be the case. So the next thing we need to do in order to find the covariance is to find the values that these random variables can take and remove the expected value. So I'm just going to type y/x minus mu. So what I'm going to do here is I'm going to take that particular value that y can take -1, and then I'm going to remove the expected value of y. So removing that, I have equal to this, removing expected value of y, a2 minus d8. And let's do $, and I can just copy it down. So of course, since the expected value is 0, these values will be the same. Here I'll do the x value minus its expected value. So it's -1 minus, and the expected value is in D7. Do a $sign on the D7. So if I copy that here. To find the covariance, what I need to do is to take the product of these possible numbers. So I take the product of the corresponding number here and here to get a value here. So it's this times this. Similarly, I do exactly the same thing here. This times this. Here I do this multiplied by this. And here we do this multiplied by this. Let's do just easier to see what we're doing. Put a little box around that. So once we have calculated these products, the covariance is simply the weighted average of these numbers, weighted by these probabilities. So the covariance between x and y, let's write it here, covariance x comma y. So let's write it here, cov x comma y instead. It's the weighted average of these four numbers. So I do this number equal to this number, weigh it with this probability, plus this number, weigh it with this probability, plus this number, weigh it with this probability, and the final one, weigh that with this. In this particular example, since all the probabilities are the same, what I will get is just the average of these four numbers. And the average of 1 minus 1 minus 1 and 1 is 0. So in this particular example, the covariance between x and y is 0. And if I didn't get that, I made a typo somewhere. And the typo is here. It should be a plus, not a multiplied by. So now the covariance is, as it should be, 0. So now we can play around with this and see what affects the covariance. So let's change the probabilities such that we have 0.3 on the diagonal and 0.2 on the off diagonal. So first check that all these probabilities do indeed sum to 1. you can see that the probability for x is the same, half for both of them, half for both of them. So the expected value has not changed, that's still 0. But the covariance will change because now there is a larger probability on the positive numbers, 1 and 1 here, and a smaller probability on the negative numbers. So that means that the covariance will be positive. And the way to think about it is that in this particular case, there is a relationship between them. Whenever x tends to be large, that is, whenever we are here, y tend to be large. It's much more likely then for y to be 1 than to be minus 1. And similarly, whenever x tends to be small, y tends to be small because there is a bigger probability that y is minus 1 in that case. So that's also the recipe for creating an example with a negative covariance. All we have to do is to reverse these 0.2 and 0.3 cells. So if we instead put 0.2 on the diagonal and we put 0.3 on the off diagonal, then we're not going to change the expected values. They will all be 0. So the deviations from the mean will be the same. But now, because we have a higher probability on the minus ones, the covariance will come out to be negative. In this particular case, we can see that the largest possible covariance that we can ever get is when we have a largest possible probability on the diagonal elements. So if I put 0.5 here, 50% of this minus 1, 1, minus 1, minus 1, 50% here, then there's nothing left for the case when they have different signs. In that case, we have the maximum value of covariance, which in this example is 1. That's not a hard limit. It could actually be greater than 1 in other examples, but for this case, it's 1. And by just reversing this, putting zeros on the diagonal, we see that the covariance can go all the way down to minus 1. But we can actually see a couple of more things. For example, what happens if one of the random variables is a constant? Let's say that y is a constant. It can only take the value plus 1. Well, in that case, this needs to be 0, cannot take the value minus 1, and we put, let's say, 50% each here. So we only have two cases. X is 1 and x is minus 1 and y is 1. X is plus 1 and y is 1. Those are the only possible cases. In that case, the expected value of x is still 0, 50-50 between minus 1 and 1. The expected value of y is now, of course, just 1, 50% 1, 50% 1. Which means that when I subtract the expected value for the x, you get minus 2 here, but that doesn't matter because it can't happen now, and you get a 0 here. And the fact that you get a 0 here, when you multiply that with the deviations from the expected value for x, you will get 0 in these two cells. And then when you now calculate the covariance, you're supposed to take the weighted average of these four cells. You're supposed to have weight 0 on these two, weight 50% on these two, and you see that the covariance comes out to be 0. And that's an important result. When you take the covariance between a random variable and something that's constant, it must be 0. Based on this idea, you can probably figure out how to calculate the covariance in a more general setting. We just add more rows if we have more possible x values. We add more columns, sorry, the opposite. We add more columns if we have more possible x values, and we add more rows if we have more possible y values. We get a matrix just like this, but it'll be bigger than 2 by 2 with a bunch of probabilities. They'll still sum to 1. We can still calculate the probabilities for x and y random variable, so we can still create this matrix, which has the deviations from the respective expected values. And even though this will be a bigger matrix, we can still calculate it, and then the covariance will just simply be the the weighted average of these numbers that I have highlighted, weighted with the probabilities. If you move to the continuous case, then you simply just have to replace this sum that you have in the covariance with an integral. But technically it will be a little bit more messy because the covariance will be described in terms of a double sum, and the covariance will be defined in terms of a double integral in the case of a continuous random variable. Alright, so that's the a little bit difficult concept, covariance. The next one is much simpler, correlation, as it's simply a scaled version of the covariance. So in this case we still have two random variables. The correlation between them is just defined as the ratio of the covariance to the respectively standard deviations. So we're just basically scaling the covariance, and what we're doing is that we're making sure that we get a number which is between -1 and 1, and making it a little bit easier to interpret. So we have this result that the correlation is always between -1 and 1. And we have the result that the covariance and the correlation will always have the same sign, and that's because the denominator in this ratio must always be positive. We do not define the correlation if either the x random variable or the y random variable has no variance. They are also 0 at the same time. The covariance is 0 if and only if the correlation is 0. If that case happens, if the covariance is 0, we call them, well, instead of calling them uncovariated, we actually call them uncorrelated. No correlation. But a concept such as uncovariated would be correct as well, but that's never used. Here's another simple example to think about the sign of the covariance correlation, not the particular value. So let's say that we toss two dice. X1 is the result of the first die. So X1 has the range 1 through 6. X2 is the result on the second die. It has the same range. And we can assume that these are fair dice, so the probability of each outcome is the same. The probability of getting, let's say, 1 and 1 is 1 over 36, and so is the probability of any other of these 36 combinations. So what we do now is we define from these two random variables a new one. We call this y. Y is the sum of x1 and x2. So the range of y will be from 2 to 12. Y can take a value between 2 and 12. And we define a fourth random variable, which is the difference. So z will be the difference, taking the first one and subtracting the second one. So the biggest value that z can take, that's when x1 is 6 and x2 is 1, that would be 5. And similarly, the smallest value it can take is -5. So let's try to think what the covariance between y and x1, what would the sign of that one be? Well, the way that you can argue is as follows. If x1 tend to be high, that is, you toss a high result for the first die, 5 or 6, well, then the sum tend to be high. I mean, of course, there is no certainty here, but in general, that tends to happen. And it's the general tendency is enough here. So the covariance between y and x2, just like the covariance between y and x1, must be positive. the sum is definitely positively correlated with the outcome of the second die and with the outcome of the first die. So let's think of a case where the covariance is negative. Well, the one with between z and x2 will be negative. Remember that z is the difference. So whenever x2 is large, 5 or 6, z tends to be low because I'm subtracting then a large number. And vice versa. Whenever x2 tend to be high, z tends to be, whenever x2 tends to be low, z tends to be high. So they go in opposite direction and they have a negative covariance. And this little example also lets you have an example of a zero covariance, and that will be between x1 and x2. If the first toss is high, 5 or 6, that's not going to affect the outcome of the second toss in any way. The die doesn't have any kind of memory. There's no way that that can spread from one to the other. So I think this is a nice little example to carry with you to remember the sign of the covariance. A couple of issues. One is not to confuse the covariance with the sample covariance. This is the similar kind of argument as not confusing the variance with the sample variance. The covariance is a property of two random variables. I have two random variables. They can take different values. The covariance tells us how they covary linearly. That tells us something about the linear dependence. The sample covariance, on the other hand, I need a sample to calculate that. But we do have the case that in some circumstances, the sample covariance can be used as an estimator for the covariance if that's unknown. But keep them apart. The same thing goes, of course, then for the sample correlation and the correlation. So let's just put this for the covariance down. Don't confuse the covariance with the sample covariance, which is computed from a sample where you have n observations on one variable and n observation on another variable, a total of 2n. The notation we use for the sample covariance is very commonly s square x comma y, and that's something we can calculate from a sample. The true covariance, or the thing just called a covariance, is typically unknown. So that's why another symbol for the covariance between x and y is sigma square x comma y. Finally, let's talk about independence. So we're going to say that two random variables are independent if they are not at all associated. We will not discuss the actual, there is a mathematical definition of independence as well, but I'm not going to mention that in this lecture. So independent random variables basically means that they have nothing to do with each other. For example, if x is the result from tossing a die, so x has a range of 1 through 6, and y is, let's say, what you had for dinner. So y can take a bunch of values such as 1 if you had meatballs and 2 if you have pasta or whatever. Then those would be independent random variables. It's not going to affect the outcome of the die, what you had for dinner. So independence is something that's stronger than just being uncorrelated. Being uncorrelated means that you have zero covariance and zero correlation. And that means that there is no linear relationship between two random variables. You can still have a relationship between two random variables that is non-linear. And that tells us that you can have two random variables which are uncorrelated but still dependent. The other way is not possible. If they're independent, then they have nothing to do with each other. So then there is no correlation, then there's no relationship between them linearly or non-linearly. So if they're independent, they are also uncorrelated. However, if they're uncorrelated, they may or may not be independent. If covariance is zero, then there could still be a nonlinear association between them, making them dependent. So the concept of covariance can only be applied to two random variables, x and y, while the independence assumption can actually be extended to many random variables. So I can say something like I have a sequence of random variables, x1 through xn, that are independent. And that may actually mean something different than saying that x1 is independent of x2, x1 is independent of x3, and so on. We can actually make this statement for several random variables. The final point we're going to make is the relationship between a random variable and a constant. So we saw that in the little Excel exercise, that the covariance between a random variable and a constant must be zero. A constant is a constant, so it's not going to go up or down depending on whether the random variable takes on a big or a small value. So a random variable is always independent and uncorrelated with a constant.